Hey everybody, it's Mike and Sean with the Good Math Guys again. Finally getting to produce the video of why we learned casting out nines and why we learned about digit roots. You might have watched those two videos, you should have watched those two videos prior to this and asked yourself, alright, this is kind of cool, but why do I need this and how can I apply this to some more useful math? This video shows that. Okay, so I promise at the end of this video you're going to see the connection, why we learned casting out nines and why we learned how to find digit roots by using repeated addition. One thing I also would like to ask of the viewers is please like, subscribe to our channel, all that fun stuff, but more importantly, we'd really like to get some engagement in the comments section. My father and I would be more than happy to answer every single question you guys have, whether it's a positive comment, a negative comment, or just a genuine question. Or even a request. We really would like to get a little bit more engagement from the viewers so we can kind of use that to drive where the rest of our videos are going to head. With that being said, let's jump right into this and see how we use digit roots to check multiplication problems. Hey everybody, it's the Good Math Guys, Mike and Sean. Today we have a really cool video that I've been looking forward to sharing with you guys since we started our videos on digit roots. So if you haven't watched the two videos before this, the one on finding digit roots and the other one on finding digit roots by using a method called casting out nines, you're really going to want to take a look at those before you take a look at this video. It'll make a lot more sense if you watch those ones prior to this video. Basically what this video is going to show you is a method for checking multi-digit multiplication problems without having to use any type of long division. Most fifth graders and fourth graders, when they're asked to check their accuracy for multi-digit multiplication problems, the textbook teaches them that they need to use the inverse operation of that, which is division. Nothing wrong with knowing inverse operations. However, the order at which students are asked to do this is a little bit backwards to me. Students are asked to find these products and then jump into using long division to prove that they're correct, when many times those students don't even know how to do long division, let alone do it correctly. So being a fifth grade teacher, I'll tell you exactly what kids do. They're going to get their product after multiplying those multi-digit factors. They know, since it's an inverse operation, they know that it should work using the inverse operation. So they're going to take their product, they're going to divide it by one of the other factors, they're not going to show any work, and they're just going to plop that second factor up as their quotient and say, okay, it's right because it has to be right. Well, what happens if they made a mistake and they're multiplying? Then their check is also wrong, and it's just they're chasing their tails. Another thing that they'll do is they'll do the actual long division, and since they don't know how to do it as well as they should, they make a mistake there and assume that their multiplication was incorrect, which sometimes it wasn't. So this method that I'm going to teach you today, dealing with using digit roots, eliminates the entire need for using any type of division to check your multiplication. So if that doesn't excite you, I'm not quite certain that you have a pulse. So without further ado, I've got three separate multiplication problems here that have been solved already for you, just for the sake of saving us some time. And I'm going to use digit roots to check the accuracy of these three multiplication problems. Again, if you watch the two previous videos, you can use a method called repeated addition to find digit roots, or you can use a method called casting out nines to find digit roots. My personal preference is when you have shorter problems like these two here, where it's a 2x2 problem, then it's not as necessary to use casting out nines because you don't really have that much addition that you need to do. So for this first factor, we have a 4 and an 8. 4 plus 8 is 12. 12 is not a digit, so we need to continue with our adding. 1 plus 2 is 3, so the digit root of this factor is 3. The second factor is 32. 3 and 2, when you add them together, give you 5. 5 is a digit, so we don't need to add any further. Now, very important, since this is a multiplication problem, we are going to multiply the 2-digit roots. 3 times 5 is 15, which again is not a digit, so we find the digit root of this, which 1 plus 5 is 6. This 6 right here is very, very important for this particular problem. If our product has a digit root of 6, we can safely say that all of our multiplication was done correctly. So for this one, since I'm dealing with more than 2 digits, I am going to try to eliminate any of the 9s that I might see. And if you're looking carefully, there's several 9s you could see. You could use the 3 and the 6 here and get rid of these two, leaving you a 1 and a 5. But I prefer to do this 5 plus this 3 plus this 1 to get that 9, leaving only this 6. So the digit root of 1,536 is 6. And again, since this magic number here matches, we can safely say that our multiplication here was done correctly. Let's move on over here to the second example. 67 multiplied by 46. We get a product of 3,082. Again, if the digit root here times the digit root here gives us a product with that digit root that equals this one, we're good to go. So 6 plus 7 gives us 13. 13 is not a digit. 1 plus 3 is 4, so the digit root here is 4. Here, 4 plus 6 is 10. 10 is not a digit. 1 plus 0 is 1, so our digit root here is 1. 4 times 1 is 4. 4 is a digit, so we leave it alone. Our magic number here is 4. If I can get a digit root here of 4, we're good to go. I don't see any 9s or anything here, so we'll just do our repeated addition. 8 plus 2 is 10, plus 0 is obviously 10, plus this 3 is 13. 13 is not a digit, so when we add 1 plus 3, we also get a digit root of 4, exactly like we should. Now, before I move on to the next one, I just want to let you know what a teacher or myself or Mr. Rooney Sr. would expect here. This written part here, once you get really good at this, I know a lot of you are looking at this like, why all this extra work? This all, when you're good at it, trust me, it can be done mentally. It takes practice, just like anything in math. You have to practice. But again, lots of my students are good enough at doing this to where they do their checks in their heads. There was a case where I've had to ask them, okay, show me. They were able to show me. This works way better than the division, where they just know inverse operations are supposed to work. So this is way more useful in terms of me understanding that they know how to multiply and they know how to use these digit roots. This problem here is a 3-digit by 2 digits. So this one's obviously more geared towards your 5th graders. 4th graders might see this, they might not. Again, you can combine what strategy you want to use to find the digit roots here. I see a 9 right away, so why not just get rid of it? So we get rid of this 9, leaving us with a 4 plus 1 for a digit root of 5. Over here, we have a 3 and a 5, which is going to give us a digit root of an 8. And again, since we're multiplying here, we multiply these two, and we get a product here of 40. 40 is not a digit. 4 plus 0 is 4. So our magic number, just like the last problem, is 4. So with this product, 14,575, if I get a digit root of 4 here, our math was done correctly. Again, going to try to cast out some 9s if I can see them. I see one right here with this 5 and this 4, leaving me with this 1, this 7, and this 5. So 1 plus 7 is 8, and 8 plus 5 is 13. 13 is not a digit, so we would have to continue. 1 plus 3 is 4, and again, they do indeed match. So again, this video is a method for checking multiplication accuracy by using digit roots. No long division needed, no memorization of inverse operations and the fact that they're supposed to work. Again, this is a really, really cool little trick that, again, you take practice with it, you'll get really good at it. Don't forget that you can use either method, the casting out nines or the repeated addition, to find your digit roots. But again, hope you guys really enjoyed this. I know this is one of my favorite videos to share because not very many people know this. So I really encourage you, if you never knew this before, share it with your parents, share it with your aunts, share it with your brothers, your sisters, your grandmas, your grandpas. I'm sure they will find this very interesting. And you have the added bonus of teaching them something they probably don't know. So who doesn't like doing that? With that being said, that's it for this episode. Don't forget to like and subscribe our channel. With that being said, we'll talk to you later. Bye-bye.